So let's come to the sum of geometric progression. This sum requires a bit of algebraic manipulation. It's not that intuitive, not that direct or easy as with the case of an arithmetic series, but still it's not too difficult to grasp. If I explain it to you, you will understand very easily. Okay, so I'll just go through the steps of how we derive this formula, and then we'll apply this formula to certain problems. So here I have written the expression for sum S of a general geometric progression AR square all the way to AR power n minus 1. This sum is basically the geometric series. Remember that the terms form a sequence, the sum forms a series. Okay, what I'm going to do is I'm going to write this term again, but I'll shift all the terms by one spot. So the first term I'm going to start with is here A, then AR, then AR square, all the way till over here. I'm going to have AR power n minus 2. This is the second last term, and AR n minus 1 last term. You will see why I'm doing this, so it will become clear in just a moment. Now what I'm going to do is I'm going to multiply the second equation. So if this is the second equation, I'm going to multiply the second equation with R. So R into second equation. Okay, let's see what this gives. So I have R into S on the left hand side is equal to AR. Now the first term has become A times R. Since I'm multiplying R with every term, as I'm multiplying with the entire right hand side, the second term will become AR square, then AR cube, and all the way to AR power n minus 1, and the last term will be AR power n, because everything has gotten multiplied by R. Okay, so on the left hand side I have R into S, on the right hand side I have this expression, what this was, every term multiplied with R. The whole thing I basically multiplied with R. Okay, and this is what I got. So now let me write down S over here, which is A plus AR square plus AR power n minus 1, and RS over here, which is starting from the second spot. I'm starting from the second spot and writing it down. AR square. Over here I'll have AR power n minus 1, and over here I'll have AR. Okay, I have AR power n because remember this is RS over here. Now let me subtract this. So this is basically 1. I'll call this the third equation, as the second was this one. So 1 minus 3, I'm going to do 1 minus 3. Okay, let's see what this gives. So all these terms, since there is a minus sign now, minus will come minus here, minus here, minus here. This will cancel with this will cancel. So all subsequent terms will go on cancelling, this will cancel. And in the end, what I have is, on the left hand side, I have S minus RS. And the right hand side, I have this first term, A. And negative of the last term present over here. So A minus AR power n. This is what I have. Okay. In this manner, I'll take S common over here. So S into 1 minus R on the left hand side is, over here I can take A common, A into 1 minus R power n. So S is basically A into 1 minus R power n divided by 1 minus R. This is the formula for sum of a GP. Okay, you'll have to remember this formula. Okay, before proceeding with questions, I'll just give you a little bit of general knowledge about numbers. So first of all, if this sum which I just got as A times 1 minus R power n by 1 minus R, if I multiply both the numerator and denominator with minus 1, so in the numerator also minus 1, denominator also minus 1, what I get is S remains the same because I'm multiplying by both numerator and denominator with minus 1. So on the left hand side I just have S. This is equal to times R power n minus 1 by R minus 1. Okay, so if this is easily explained, if I take a factor like x minus y and multiply minus 1 with this, so you have minus x plus minus 1 into minus y, that is minus x, plus y, that is y minus x. So basically it has, the terms have reversed. The terms have swap places, x and y. Same thing I'm doing over here in the numerator as well as the denominator, and I have this also as a sum. So typically if the common ratio is less than 1, we take this sum. If the common ratio is less than 1, we use this. Why? Because both the numerator and denominator are positive in that case. Numerator and denominator are both positive. If r is greater than 1, common ratio is greater than 1, we take this sum. Again, because numerator and denominator are both positive in that case. Okay, now coming to, as I said, some general knowledge about numbers. What happens if you take half power 5 and I keep increasing it? I say I take half power 7, then I go further, I go half power 10. So this number is 1 by 32. This number is 1 by 128. And this number is 1 by 1024. Okay, so we can see that the numbers are getting smaller and smaller as this power is increasing. Although the powers are increasing, the number is getting smaller and smaller and smaller. Now imagine if I take a number something like half power 100. Okay, already we have 1 by 1024, which is lesser than, this is lesser than 0.001. Half per 100 will be far lesser than this 0.001. It will be such a small number that I can assume this to be nearly equal to 0. Okay, so I'll explain the purpose of this. Sometimes what happens is we have to find the sum of an infinite GP. Okay, so let's take an infinite GP like 1 half, 1 by 4, 1 by 8, and so on. So to find the infinite sum of the GP, we know that n is infinity. We have a as 1. So 1 minus r per. Here r I can get by dividing the second and first term. So 1 by 2 whole divided by 1, which is half. This is r. Okay, so 1 minus r per n. R is half per t divided by 1 minus half. So this is basically half per infinity. As I said, see, half per 100 is a number which is so small we can assume it to be 0. Half per infinity is even smaller, and I'll say that it is just outright 0. 1 minus 0 by 1 minus half. This gives me 1 by 1 minus half. This is 2. So although the number of terms is infinite, the sum I'm getting is a finite number. Now let's try doing the same for r is greater than 1. Okay, so I'll start with the series 1 plus 2 plus 4 plus 8 and so on. As I know, the sum is a times 1 minus r per n by 1 minus r. In this case, since r is greater than 1, I'll write it as a times r per n minus 1 by r minus 1. Okay, now if I'm going till infinitely many terms, I have the sum as a is 1, r per n, so r is 2 by 1, which is 2, so 2 per infinity minus 1 by 2 minus 1. This is 2 per infinity minus 1. So the numerator in this case is actually very large. In fact, we'll just say that it's infinity. So the sum to infinitely many terms of this geometric series is infinity because the common ratio is greater than 1. The terms are, you can see how fast the terms will start jumping. We're going from 4 to 8, 8 to 16, then 32, and so on. We'll be jumping very quickly, and eventually we'll get numbers itself which are so large that their sum is definitely going to be extremely large. So we have infinity as the sum. Okay, so if the common ratio of a GP is less than 1, if R is less than 1, then sum of GP, this is sigma symbol notation for sum of GP is basically finite. Sum of GP is finite. Okay, and if R is greater than 1, then sum of GP is infinite. This is now this for an infinite GP, meaning that the number of terms is infinite in both. So S infinite in both. Okay, if n is finite, then the sum of both is finite. If n is finite, then sum of both is finite. Okay. Also over here, r being less than r being greater than 1, it's between 0 and 1. So I'm assuming the value of r between 0 and 1. Here, what happens if r is less than 1? So if r is something like, say, minus half, okay, let's see what happens to this GP, infinite GP. We'll look at what happens to the infinite GP. Let me start with the term 1. The next one is going to be minus half. The next one is going to be plus 1 by 4. Why plus 1 by 4? Because I have minus half squared. Okay, so this is plus 1 by 4. The next term is going to be minus 1 by 8. So I'm going to have alternating. I'll write it down clearly over here. 1 minus half 1 by 4 minus 1 by 8 1 by 16 minus 1 by 32. So let me try to for sum in this case. I have a times 1 minus r power n by 1 minus r. So that is a is 1 minus r. So over here you can see what r is. R is actually minus half. Okay, if I divide second term with first term, minus half by 1, that is minus half. So r is minus half. I have 1 minus half power n divided by 1 minus half. So you see what is happening in the numerator. In the numerator, I have minus half power n. The thing is, the denominator of this 1 by minus 1 by 2 power n, if n is very, very large, will be extremely large, because in the denominator I'll have 2 power n, okay, 2 power infinity. So this is still 0. This term is still 0. I basically have 1 minus 0 by 1 plus half. The minus and minus over here become plus half, and I'm left with 1 by 3 by 2, that is just 2 by 3. So this formula holds good even if r is negative. And again, so basically this, right, this is for r greater than minus 1 and less than 1. So I can further write down this equality. So if for a sum of infinite GP such that r is between minus 1 and 1, the sum is finite. Okay, infinite GP, I mean n is infinity and r is between minus 1 and 1. The sum of the GP is finite. And if r is less than minus 1, again I will get the same thing. Sum of GP is infinite if n is infinite. So let's look at a sample problem based on sum of GP. Over here we have, so the question says the sum of an infinite GP is 15 and sum of the squares of the terms is 45. We'll quickly just write this down. Sum, so if I take the first one as a and the common ratio is r, the GP is a plus ar square, and since this is all the way to infinity, ar per, okay, just writing for the sake of understanding right now, this is equal to 15. And if I square every single term, a square plus ar whole square plus ar square whole square, as well, this is 45. Okay, and we have to find the GP. So finding the GP basically means you find a and you find r, you're done by you have basically found the GP. Okay, so I'll quickly write down the sum of this, sum expression for this. So first of all, you need to understand that if it is an infinite GP with a finite sum, as I said before, infinite GP with finite sum. What does this mean? This means that r is between minus 1 and 1. Okay, this is from what I just explained. If it is an infinite GP with finite sum, r lies between minus 1 and 1. Okay, so if r is between minus 1 and 1, the sum formula, what was the sum formula? 1 minus r power n into a by 1 minus r. Since this r simplifies to 0, we are just left with a by 1 minus r. So this is what the sum becomes. So the very first equation, I'll mark this as first, this is the second equation. So the first equation is basically now a by 1 minus r. is 15. And the second equation, in the second equation, the first term is a square. Okay, also as I said, if r is less than 1, r square is also less than 1. I have a square by 1 minus, here the common ratio I can get by dividing the second term by first term. So the second term is a square r square, first term is a square, so the common ratio now is r square. Okay, 1 minus r square, this is equal to 45. So these are the two bits of information that I have to work with this and get my answer. So let me just divide 2 with 1. So I'm going to do 2 divided by 1. Let's see what that gives. So this is a square by 1 minus r square divided by a by 1 minus r, which is nothing but a square by 1 minus r square into the reciprocal 1 minus r by a. Now let's just start cancelling these terms. A cancels. So 1 minus r square is basically, so this is a by 1 plus r into 1 minus r. I have just factorized 1 minus r square into 1 minus r. So what I'm left with is just a by 1 plus r. And the right hand side, or dividing 2 by 1, the right hand side is basically 45 by 15, which is 3. So both the right hand side, if I divide, I get 3. So a by 1 plus r is equal to 3. I have the first equation, that is a by 1 minus r is 15. Second equation, a square by 1 minus r square is 45. And third equation which I just got, that is a by 1 plus r is 3. So I have to use this much information to get a and r. What I'm going to do is I think if I just use 1 and 3, it seems enough because there's both a and r in both these equations. See, we have 2 variables and actually we have 3 equations. I'm going to use the simplest 2 equations to get the answer. 2 equations and 2 variables. How do we solve this? We basically use one equation. I'm going to use this equation to substitute to get one variable in terms of the other. So now if I take this 1 plus r to the other side, I have a is equal to 3 times 1 plus r, and I'm going to make this substitution in 1. Substitute this in 1. Okay, so substituting in 1, I have a by 1 minus r now becomes 3 times 1 plus r, because I'm substituting a as this value. 3 times 1 plus r by r is 15. This will just give me a linear equation in r. I have basically 3 plus is equal to 15 into 1 minus r. Taking this denominator to the other side, this becomes 3 plus 3r is 15 minus 15r. Now I'll take r terms on one side and constant terms on the other side. I'll get 3 plus 15, so left hand I have 18r. Over here I'll take this 3 to the other side. I have 15 minus 3, which is 12. So r is 12 by 18 is equal to 2 by 3. I got the value of r. Now let's substitute r back in over here in this equation. So I have a is equal to 3 times 1 plus 2 by 3, which is nothing but 3 plus 3 times, I'll take LCM over here. I have 3 plus 2 by 3, this 3 cancels, and I have 3 plus 2 5. So a is 5. I got the GP 5 into 2 by 3, so that is 10 by 3. Then 5 into 2 by 3 into 2 by 3, so 10 by 3 into 2 by 3, that is 20 by 9. 20 by 9 again into 2 by 3, that is 40 by 27, and so on. This is the GP. We can always check our answers. We can check our answer by putting the same thing in the second equation. Let's just put it once in the second equation. Second is this one. I have a square. Now a square is 5 square, that is 25, upon 1 minus r square. R square has now become 2 by 3 square. 2 by 3 square. So this is 25 by 1 minus 4 by 9, which is 25 by 5 by 9. So this 525 comes 5, and I'm left with 5 into 9, which is 45. Okay, so that is what is given on here. This satisfies. So this is basically the GP that we were looking for.